The one with the
Oh,
all red and stuff?
wait,
Or
let me answer this question and I'll get your question. Because she's been waiting since like 5 minutes, I think. So most of the equations are going to be given, except some of them you'll have to derive. Like the temperature, dependence ones, you'll have to derive those. So like delta G is equal to whatever, whatever. But the ones that temperature equals, those you have to be able to derive. Okay. All right, what were the other questions? We only did one buffer lab. Um, is do you remember using the pH meter?
The indicators?
The indicators lab?
The doing all that? That one?
Yeah.
But we signed up for that one in our lab manuals.
No, that one I wanted a paragraph saying, remember I changed the experiment a little bit. The experiment was make a buffer and then add X milliliters of acid to it and read the pH. And then, to the other half of the buffer you made, add X milliliters of sodium hydroxide and then read the pH. But I didn't like that. So what I asked you to do was make the buffer, split it up into two, and then continually add acid and watch the pH. And so what a buffer should do is it should try to maintain the pH. But eventually you'll hit a point where it fails. You've exceeded the capacity of the buffer. Did that happen? No? No, you're supposed to keep adding until something. And so you just keep adding and adding and adding. Just to see what happens. And basically, I wanted just a paragraph of what happened with the buffer. Well, if you didn't do that, what did you do with the buffer? Did you take any observations at all? No? It was a very short lab. All you did was... What's that? Yeah, but we didn't even use the indicators. We skipped all that stuff because it was too time consuming. So I shortened the lab. You did the indicators? But you didn't do the buffers.
You wanted to use cyclic acid based on the buffer.
Well, do you have the lab manual? Does anybody have the lab manual? Yeah, that. Okay. The lab is called hydrolysis of salts and pH of buffer solutions. I wanted you to focus on the buffer solution. Well, measure. It was the twofold. One was just to use the pH meters for the first time. How to calibrate that with a pH 4, pH 7 buffer. And the other was just how do you take a measurement. Fill up. There are a whole bunch of different solutions, and then you just measure some of the solutions. You didn't have to measure all of them. But they had sodium acetate, zinc chloride, ammonium chloride, potassium aluminum sulfate. Potassium aluminum sulfate, I talked about that one. You might have that in your notes because potassium aluminum is an acid and sulfate is a base. And so this one was tricky because what is the pH of this one? Was it acidic or basic? So look back in your notes and look for potassium aluminum sulfate and then and see what we have. But the last part of this lab, you had to make a buffer, and the way you made the buffer was you mixed, let's see in the procedure here. You mix sodium acetate trihydrate and acetic acid. And so it's an acetic acid acetate buffer. And then you divide it into two beakers. Like half of it goes into one beaker, half of it goes into the other beaker. One of the beakers, you added acid to it. But the procedure just says add a fixed amount of acid. Well, adding a fixed amount of acid doesn't really tell you how the buffer behaves. All it says is you add a fixed amount of acid to it, you measure the pH, then all you know is this. The analogy is like all you know is one tree in the entire forest, but you don't know how far the forest goes, right? And so what we wanted to do was to see how far that forest goes, like how far until the buffer collapses. And so what I wanted you to do was continue adding acid drop by drop by drop, or you could have gone faster, but just continue adding acid while watching the pH meter and seeing what happens to the pH as you continue to add the acid. You know, and hopefully what I wanted you to do was keep adding it until it doesn't take very long, until the buffer fails and the pH changes dramatically when we exceeded the capacity. I wanted you to do that on the acid side and the base side, and this buffer, you know, acetic acid is a stronger acid than the base acetate, and so this buffer starts at around pH 4, you know, 4 to 5 or whatever. Right, but if you only do 1 milliliter, right, you only see one tree. You don't see how far the buffer goes. And so, in other words, I wanted you to see the forest rather than one tree. So that's why I wanted you to continue to add acid. Do you remember that? And then at the end of this, I said, well, just write a paragraph what happened with the buffer. The paragraph that what happened with the buffer is, you know, well, you added acid, and all you can say is this in a sentence. I added acid, and I stopped at this many milliliters, and this is what happened to the pH. The pH stayed fairly stable the entire time, or the pH continued to decrease, or the pH continued to increase, or, you know, just tell me what happened from this to that. How did the buffer behave with added acid and added base, you know? Well, actually, that's pretty much all I wanted for this one, was a paragraph stating how the buffer behaved. You could describe it. You know, some people love to write and write like detailed. You could, you know, or you could keep it minimal, a sentence. You know, oh, pH changed from here to here, this many milliliters. And if you stopped early, you know, then you must still be in the buffer region. All right, so let's see. Some people have just followed the procedure. That's okay. If you follow the procedure, I'm not going to knock you for that. So 1 milliliter. But 1 milliliter really doesn't tell you much. You know, if you just add 1 milliliter, who knows what the capacity of that buffer really is. You know? See what Joy did. All right. Are there any other questions about this buffer?
Yes, so now that you explained what you want us to have, whatever, when you want to turn in.
Well, a lot of people have already turned it in. Maybe not in the afternoon, but how much time do you need to finish it?
I want to let it come up.
All right, then turn it in next week if there wasn't this.
Thank you.
Yeah, come on. Well, I don't know. Did you turn in the kinetics lab?
Yeah.
Did you turn in the visual Mintech lab? Did you turn in the Spartan lab? Okay. To be on the safe side, you know, all the labs are due, basically. You're going to turn in your notebook too, but you're going to turn in your notebook at the end of the semester. I'm going to just check it off for observations. That's it. Just see. Have you been... So if you have most of your observations, it's not worth that many points, but it's worth some points. It'll be due at the end of the semester. But officially, all the labs are supposed to be due a week after, but I fell behind in the grading, so I don't want a whole backlog of lab reports, so that's why the due date hasn't been totally clear, but some people have been just turning in a week after, which is fine. I'll just collect it. None of them require write-up except for 2 of them. The others are just like a simple paragraph. So, for example, this, what was it? The not the Spartan, but the visual Mintac. The visual Mintac, I just asked for a paragraph. You know, and a paragraph. I left it open-ended like this so you could just talk. You know, for the visual Mintac lab in the past, I had one person write 3 pages worth of stuff for it, because they're so gung-ho about the visual Mintac, but I didn't expect that for everybody. And so, but I don't, you know, if they want to write that, that's fine. I'm not going to say just turn in 1 sentence or 1 paragraph, you know. And other people just turned in a sentence, you know, about visual Mintac. And so, you know, this is just going to be graded on the, based on that. So the visual Mintac is like, you know, have you done like a comparison and contrast or something like that? Or, you know, if you do something similar in a paragraph, that's fine. Something like that. Mm-hmm. Imidazole, what you have to do for imidazole is this. You have to figure out all the hydrogens in the structure and then rank their chemical shift. And so you want to go from the smallest chemical shift to the biggest chemical shift. In other words, increasing chemical shift. And so what do we want to do with the chemical shift? Well, you know, chemical shift of 0, is that shielded or de-shielded? In other words, is it shielded or de-shielded? A chemical shift around 0. No. It would be on the right. A chemical shift is 0. It's an arbitrary 0, and it's set by TMS. TMS is called tetramethylsilane. The special thing about tetramethylsilane is that the hydrogens are heavily shielded or the hydrogens are heavily de-shielded. Now this is in that PowerPoint, but PowerPoints go by pretty fast. You probably don't have it. the PowerPoint on this. Did I show this PowerPoint?
Yes.
Yes? No?
Thursday? No.
Did I show this last week? Oh, maybe I didn't. All right. Basically, in nuclear magnetic resonance, the hydrogen atoms nucleus acts like a little tiny bar magnet. If you take this molecule and put it into a big external magnetic field, what happens is the magnet in the hydrogen atom interacts with the magnet in the external field. Right? And there's one thing that can interfere with that. Let's skip all this stuff. The one thing that interferes with that is the electron cloud surrounding the hydrogen. And so if the nucleus is that kind of red dot in the center, you can see it's misaligned because this blue arrow is representing the external magnetic field. These are gigantic magnets. They're usually superconducting magnets that they put these in, so they're huge. And you want to generate a strong external magnetic field because the magnet of hydrogen is so weak. And so the stronger the external magnetic field, the easier it is to detect the tiny magnet, which is the hydrogen atom. But this electron cloud does something called shielding. It shields the blue arrow from the black arrow. And the more electron density you have, the more shielding you have. There are things that suck electron density away from hydrogen atoms. One thing that sucks electron density away from hydrogen atoms are electronegative atoms that are bonded to it. And so if you have an electronegative atom bonded to this, what happens is it pulls the electron density away from the nucleus and causes what's called de-shielding. We can actually measure this using NMR spectroscopy, or magnetic resonance spectroscopy, or nuclear magnetic resonance spectroscopy. And so this is basically it. If you look at this, there's more shielding, which means there's more electron cloud around that nucleus. This is less shielding, there's less electron cloud, and that's going to alter the energy of the interaction between the two magnets. And so they're both hydrogen atoms. It's just the electron density, that's surrounding the nucleus that increases or decreases, the de-shielding, shielding, or the energies. And so if we look at this, a hydrogen bonded to carbon is going to have a different level of shielding than a hydrogen bonded to oxygen. And so when you look at this, which one is more shielded, which one is less shielded? Well, the more shielded one will have more electron cloud around the hydrogen. So which one would have more electron cloud around the hydrogen, and why? Yeah, the carbon. The carbon's going to be more shielded because it's less electronegative. It's going to not pull as much of the electron cloud towards it, whereas oxygen is much more electronegative, so it's going to have a pulling or an attraction to the electron cloud, and it's going to pull the electron cloud closer to oxygen than hydrogen. We have a color coding for this. The color coding we use in Spartan is this. This hydrogen would be much more green or blue. This hydrogen would be much more red. Or, is that right? No, I have it backwards. I have it backwards because red means negative. And so this one would be much more blue, this one would be much more red. Green would be kind of neutral, so this could be green too because this is a fairly nonpolar bond. The way we measure the energy is we don't measure the energy in terms of energy, we measure the energy in terms of chemical shift. The chemical shift is given in weird units of ppm, parts per million. I'm not going to get into the reason why, but essentially this is the energy that we're looking at, or it's related to the energies. And so over here, this is what we call upfield. Down here, we call this downfield. And so the further right we go, that's the further upfield, and the further downfield. And you can see that the hydrogens here, these are all hydrogens, and these are all measuring the little magnetic moments in the hydrogen, but the hydrogens are going to have different chemical shifts depending on the level of shielding and de-shielding that they experience. Now the scale is going to be arbitrarily set to 0. And so we set an arbitrary 0 here to keep the numbers simple to read. The arbitrary 0 is called TMS, which is our standard here. It's tetramethylsilane, which is heavily shielded. And so these there are hydrogens potentially more shielded than this that could have negative. But most of the chemical shifts are going to be positive. So for example, this one, acetone, has a chemical shift of 2.1 ppm. These are these methyl groups bonded here. But if you look at nitromethane, it's 5.2 ppm. And then over here, this is kind of like this, what is that? This is trichloro, and it's almost like trichloroacetic acid, but it's missing an O. We call these aldehydes. And so this is like a trichloroethanol, or trichloroacetaldehyde. Anyway, that's going to have a pretty big chemical shift, a 10 ppm chemical shift. And so what does that mean? Well, that means that must be heavily, what, de-shielded or shielded? No, de-shielded. Shielded is upfield, de-shielded is downfield. Benzene's kind of interesting, but benzene, you know, because of the delocalized pi bonding network, you know, there's room for electrons to go. And so this aromatic, we call these aromatic hydrocarbons. These aromatics have different electronic properties than the normal hydrocarbons. Normal hydrocarbons are called aliphatic hydrocarbons. Uh-huh.
You said aromatics. Is the same thing as esters?
Is the same thing as what? Esters? No. No, esters don't have to have any. Esters can contain aromatic groups, but they don't have to. Esters are like this. If you take acetic acid and take the acidic hydrogen off and put a methyl, then we just form the methyl ester of acetic acid. And so it's a bit different. Ester bonds also occur in things like, you see ester bonds. Ester bonds, you know, have you heard about the arsenic-based life monolate? You know, most life relies on phosphate and phosphate esters. Have you ever heard of phosphate esters? It's like phosphoric acid, but you remove a acid hydrogen and replace it with some other group, another phosphate, for example. But arsenic was thought to have replaced phosphorus in some life forms, in these bacteria that occur in monolate. But a lot of people were saying, you know, an arsenic ester bond is way too weak. It's way too easy to break. It wouldn't be stable. So they should rethink that data. But anyway, it's a little bit different. Aromatics are always going to have this alternating double bond network. And it doesn't have to be a 6-member ring. It could be different ring structures, or it could be different chain structures. But what all aromatics have in common is they have a alternating double bond network. Alternating double bond network, all the p orbitals are aligned because they're all perpendicular. All these aromatics are flat. They're planar molecules. The sp2 are going to form these in the plane, but the p orbitals perpendicular to the plane all stick out and they're all lined up, and then you can delocalize the pi electrons over large parts of the molecule. So it gives them unique properties. And so benzene's a little bit unique because it's not a normal hydrocarbon, it's an aromatic hydrocarbon. But if you look at a normal hydrocarbon, you know, they're around here. Anyway. So that was the PowerPoint. So basically from the PowerPoint, you should just get something. There's something called chemical shift. Chemical shift is, we can measure in an instrument called an NMR or an MRI. MRIs measure chemical shifts as well. But MRIs are a little bit different because they have inhomogeneous magnetic fields. And MRIs are just looking at the hydrogens in water, but they change the field strength so they can look at where the three-dimensional position of that water molecule is. So MRI, NMR, they all work by the same principle. But anyway, going back to this, what we're going to do is we're going to just, because Spartan, what does Spartan do? Spartan maps out the electron density in a molecule. So if you map out the electron density in a molecule, you should be able to calculate the chemical shifts. And so what Spartan does is it calculates the chemical shifts that it expects for each of the hydrogen atoms. And so when you set up your calculation, you have to check the display NMR. And that way it will calculate all the NMR chemical shifts. This is after you build the molecule. And building a molecule is not so easy. A lot of people are struggling with it and still struggling. A lot of people haven't even finished it. So we're going to continue it on Thursday too, just to build the two molecules, right? Okay, once they built, some people got lucky. They built it and the calculation worked and they were finished quickly. But some people, for some reason or other, just is not working. But anyway, here we're going to list all the chemical shifts and rank the hydrogens in order. And so then you compare those to the structure. You know, you look at the structure and then see where those hydrogens are located. And does it make sense, you know, that, does that make sense that it's like this, you know, whatever that structure was. And so you look at the hydrogens here and then see, let's say this is the protonated form. So this whole thing carries a positive charge here. You know, and so looking at the structure and then comparing it to the chemical shifts, does it make sense that, for example, this hydrogen is the most de-shielded of them all, and the most shielded of them all is this hydrogen, or these two hydrogens? And so you're going to look at the NMR data and look at the structure and then look, you know, is that what you would have imagined, or is that what you would have visualized for the electron cloud in this molecule, how it's distributed based on the atoms that make it up. And so this one, I did not ask for a paragraph, so for this. This one is very simple. Just, what's that? Yeah, just write it down, the chemical shifts, and draw a little structure showing which hydrogens are which. And then C, does it agree with what you would have predicted for the chemical shift? Could you predict which one should be furthest downfield and which one should be furthest upfield? You know, does that agree with your prediction or not? I didn't ask for this because, in other words, you don't have to write a paragraph for this. You just turn in the numbers. But some people have thought about it because the numbers don't make sense. Let's see. I left them in my office. A lot of people finished it already. Two molecules. Actually, one molecule and one ion. You know, the protonated imidazole and the imidazole. You should take a look at what happens to the chemical shift. You know, when you go into organic chemistry, then you'll do a lot of NMR, because NMR is one of the most powerful techniques in organic chemistry. And so this is a little bit of an introduction to organic. And so I eliminated most of the entire lab except for this NMR part, the calculation. So that's all we're going to do for this. All right, so does that answer your question about today's lab? Or, you know, started in?
Professor, can you run like a checklist of which lab do?
Okay. Um, we have one more big lab due. Which one is that? Yeah, pH titration. I'll talk more about that in the computer lab. Okay, are there any other questions about the lab stuff?
Can you answer my question on curiosity? It's like, how do you calculate the H plus in the original?
I did. I answered it today. But I'll just tell you what the answer was. The answer was, this is not required, so you don't have to do it. Just don't do it. Yeah, you don't have to do that. Calculate that.
That's what the grants are.
The gram plot is not required, so that's why I didn't talk about it at all.
What about if we do it for extra?
You could do it for extra credit, but if you do it for extra credit, you'll have to figure it out yourself.
We already tried.
You already tried?
Yeah.
Did you look at the gram plot tutorial on the online? No? All right, well, we're not going to the computer lab yet because I need to do a little bit of catch up here. Posting what? The PowerPoints are, you could download these PowerPoints. Do you have a mastering account? Yeah.
What if we don't have
If you don't have mastering chemistry?
Mine expires this summer,
All right. How many people don't have a mastering chemistry? All right, let me see. Yeah, this is a new chapter. This is chapter 20, but we already talked about this. Chapter 20 deals with electrochem, and so we're done with chapter 19. And for electrochem, it's just redox chemistry. So over here you can see copper in a silver nitrate solution. All this stuff, these are tiny crystals of silver. Silver forms needle-like crystals, so it looks like a fur. And so these are just tiny slivers of silver. Over here, these are smaller crystals. Tiny crystals of silver look black because of the way they interact with light. As the crystals grow bigger and bigger, they have that metallic mirror finish, typical of silver. Well, anyway, the silver ions are attacking the copper. And so silver ions are taking the electrons from copper and depositing silver metal. The copper, losing those two electrons to silver, form copper 2 ions in solution here. Over here, this is copper metal and Zn2+. Zn2+ is not a powerful oxidizer, not powerful enough to oxidize copper, so no reaction there. But in electrochem, we don't want the electrons transferred directly, which would be happening here. Electrons going straight from copper to silver ion. What we want to do is we want to transfer those through a cell. And so this is called an electrochemical cell. An electrochemical cell, we put the oxidizer typically on the right side here. That would be the silver ions. And silver ions being the oxidizers, they want electrons. So they'll try to take the electrons from silver metal, but will they be successful? No. Silver ions will not oxidize silver metal. But if this silver metal is in electrical contact with copper metal, then silver ions can take the electrons from the copper metal, with the electrons being transported through our, what we call the external circuit here, just a piece of wire. Okay, so the silver ions oxidize the copper over here and form copper 2+. The 2 electrons travel through the external circuit over here and will reduce 2 silver ions to silver metal. So we'll get a deposit of silver metal on silver. Silver metal on silver is going to be a lot cleaner than silver metal on copper. And so it's good to use what we call an inert electrode here. If we just use a piece of copper, then we can have direct reaction here. That's not what we want. We want indirect reaction. In other words, passing electrons through the external circuit. Okay, what's the job of the salt bridge? Balance out the charge, right? Exactly. What's going to happen over here is we're generating cations. As we're generating cations, there's no anions to neutralize that charge. So what's going to happen is the anions in the salt bridge, nitrate in this case, will migrate to this beaker here and neutralize the 2+ charge generated here. Over here, the cations are being consumed to deposit silver metal, leaving the anions alone. And we can't have that, otherwise we generate too high of a voltage or space charge, so the cations will migrate to this one, potassium ions in this case. The salt bridge contains an inert salt, potassium nitrate here. We have plugs here. The plugs here are just to slow down this, because what you don't want is you don't want the silver ions, migrating or diffusing over to this beaker, because if the silver ions diffuse to this beaker, then they don't have to pull the electrons through this wire. They can just take them straight from the copper. Eventually that's going to happen. Eventually, because of entropy, the silver ions will migrate over to that beaker. But hopefully by the time that happens, this battery's dead or close to it. Okay. So anyway, do you guys remember what this electrode's called? The cathode, because the cations migrate. This one's called the anode. At the anode, the electron's always being generated. So oxidation occurs at the anode, reduction occurs at the cathode. So electrons are being generated, anode, consumed, cathode. So if we look at this cell here and measure its voltage, the voltage comes out to 0.460 volts. Let's write that up here. The voltage of this cell is 0.460 volts. The voltage has another name. How would you describe voltage? What is voltage? Voltage is a measure of what? Voltage is a measure of the pressure on the electrons moving through that wire. That pressure is caused by the pull. Silver is pulling the electrons through and taking them from copper. Copper is resisting that pull though. And so this is the net force on the electrons. And so voltage has another name. Voltage has a name EMF. Have you heard of EMF? EMF stands for what? Voltage, but it stands for what? Electromagnetic. You would think electromagnetic because EMI is electromagnetic interference, or EM rays, electromagnetic radiation, But this is electromotive force. And therefore, voltage has another symbol. We just call it E. E stands for not energy, like you'd think. E stands for electromotive force, or voltage. This E of the cell is going to be comprised of two things. When we look at it, what's pulling the electrons through? Well, there's going to be a force pulling the electrons through. That force is caused by silver ions trying to gain electrons to form silver metal. So silver ions are trying to pull the electrons through, but then there's some resistance from copper. You know, copper is not trying to lose electrons to go to copper 2+. And so this is what we end up with. A voltage is also called a potential. And so what we can say is that the cell potential is equal to the silver ions to silver, that's what we call the cathode. And so it's equal to the cathode potential plus the copper going to copper 2+ is called the anode. And so that's the anode potential. And so the cell potential is the sum of the cathode and anode potentials. Well, what are these potentials? We'd like to know the individual potentials. That is, you know, how strong of a pull does silver ions have? Well, you know, my guess is that, you know, is copper easy to strip electrons off of or difficult? Is copper a really good reducing agent or is it kind of a poor reducing agent? Copper is a fairly poor reducing agent. Copper belongs to a class of metals called the noble metals or the coinage metals. The coins, you don't want them to corrode easily. And so you want coins to be very resistant to being attacked, you know, by oxidizers. In other words, you want the coins resistant to oxidation. So for example, gold, you know, gold retains its luster because it's very difficult to oxidize. Silver stays shiny, although it can tarnish, but it's difficult to oxidize. Copper is a lot easier to oxidize, but hopefully it stays shiny for a while. Compare that to something like zinc or lead, you know, or any other metal. A lot of other metals are easily corroded. And so copper resists. So my guess is this. I get a net 0.46 volts of potential or motive force or voltage through that external source because maybe copper, you know, maybe the, oops, what am I doing? Maybe because silver ions at the cathode are pulling. The silver ions are pulling, let's say with 1 volt. The copper is resisting by minus 0.54 volts. So there's a tug of war for the electrons. And so it turns out that silver is going to win. But that's just a guess. We don't know. How strong is silver pulling on these electrons? I want to know how strong that is. Because if I know the net, you know, I don't really know how strong the individual electrode is. So if there's a tug of war, let's say there's a tug of war and the rope is moving like this, then you know this side is more powerful, right? But you don't know how powerful this side is. Because this could be a tug of war between kindergartners, you know, and this side is, yes, it's more powerful, but you know, they're kindergartners, so it's not that powerful. Versus, you know, weightlifters. If this side were full of adult weightlifters, and this side were full of adult weightlifters, you might get the same voltage, right? But the relative strengths are hugely different. And so what I want to know is, I want to know the relative strengths of each of these, but there's a problem here because I know what the total is, but I don't know what these individuals are. So this is a 2 unknown problem. I have 1 equation, 2 unknowns. So if I have 1 equation, 2 unknowns, what do I need? I need another equation. And so we try to think of another equation so that we can solve for one of these. So we can set up another cell like this. You know, in this case, copper was the anode in the previous cell. Now copper is going to be the cathode in this cell because now we're going to have copper 2 ions as the oxidizer. So the copper 2 ions are going to be pulling electrons, but they're going to be pulling electrons from zinc. This is the cell you guys built in the lab. And the zinc is going to be oxidized here. So Copper 2 attacks the zinc, pulls the electrons to the external circuit, converts the copper 2 into copper metal, and the zinc into zinc 2 plus. This has a voltage of 1.1 volts. And so how much of that 1.1 volts is due to the copper 2, and how much, that is the cathode, and how much is it due to zinc, the anode? Well, here's our second equation, but we're going to have the exact same problem because now we're going to have three unknowns. We're going to have so we got two equations now, but three unknowns because now we have the zinc thrown into the mix. And so what it boils down to is we aren't going to have a second equation. And if we have two unknowns and only one equation, then it's impossible to solve, right? Two unknowns and one equation, can we solve that? Might as well just give up. But you've seen this problem before. Do you remember where you saw this problem before? In Appendix D, saw this problem. So what did they do in Appendix D? Well, in Appendix D, what did we do? We just said, okay, we're just going to call one of these zero. We're just going to say, okay, let's call this one 0 here. So let's say at the anode, the copper is offering no resistance. If this one's 0, then the voltage, the cell voltage, is entirely due to the cathode. And so we're going to say that this pull on the silver is 0.46 volts. Okay? And so we do an arbitrary 0. Then we can solve it. And so just to repeat, cell voltages are the potential differences. This is tricky, but it's just the potentials, we'll just say, between the electrodes, and we can measure those precisely. However, we don't know how much of that belongs to each side. And so the potential of an individual electrode is difficult to establish because we have two unknowns in one equation. So it's impossible, actually. It's not difficult, it's impossible. And therefore, an arbitrary 0 is chosen. So the arbitrary 0 is chosen. So what should we call the arbitrary 0? Should we call it the copper 2 plus? Is what? This is, you know what this is? This is a shorthand way of writing these things. And so we know at the cathode, silver ions, the oxidizer, wants to get electrons to form silver metal, the product. And so this is what we call a diagram. And over here at the anode, it's copper goes to copper 2 plus. This is a shorthand way of writing that. And so we want to know what the individual potentials are, but it's impossible. So we select an arbitrary 0. But we don't want too many arbitrary zeros that you have to memorize. In fact, which arbitrary 0 have you memorized so far? Which arbitrary 0 have you memorized? Think back to Appendix D. What was the arbitrary 0 in Appendix D? Not oxygen. Close, but hydrogen. Hydrogen was arbitrary 0. And so what we're going to pick for the arbitrary 0 here is hydrogen. And we're going to call it the hydrogen electrode. The easiest thing to do is do this under standard conditions, so we call this a standard hydrogen electrode. Standard conditions just means we put a little circle here. And so this would be the standard cell potential, this would be the standard cathode potential, and the standard anode potential here. What does standard conditions mean again? Yeah, 1 molar and 1 bar and, or 1 ATM, or what about 25 degrees C? Is that standard? No. Okay, good. That's going to be a common temperature though. And so this is how you build a standard hydrogen electrode. The standard hydrogen electrode is going to bubble hydrogen gas at 1 bar in here. And it's going to have H plus AQ in solution here at 1, well, this is an activity of 1, which is 1 molar. And so we need 1 molar H plus in hydrogen gas at 1 bar. And this is the electrode here. Well, how do you get the electrons into the external circuit? We need something. I mean, hydrogen gas is not an electrical conductor. The solution is, but how do we transfer the electrons over? The way we transfer the electrons over is we use an inert electrode here. An inert electrode is going to be a piece of platinum. Platinum is often used as an electrode because platinum is a noble metal. In fact, it's one of the noblest of the noble metals because it's extremely hard to oxidize, platinum. And so platinum's even harder to oxidize than gold. And so it's very valuable for this because it's not going to react. It's going to be inert. And this is either going to feed electrons to H+, which is an oxidizer, or take electrons from hydrogen gas, which is a reducer. And so this can go either way. You know, it can be an oxidizer, or it could be a reducer, depending on when you react it with. So this is a standard hydrogen electrode here. The SHE. So if we do this, we can measure a whole bunch. And so in other words, here, let me do that first. So we'll set up a cell like this. By convention, the anode's written on the left, the cathode's written on the right. And we generate electrons at the anode, so the electrons flow left to right. We consume electrons at the cathode. So our oxidizer is over here, copper 2. Copper 2 is going to oxidize what in the SHE, or the SHE, standard hydrogen electrode? It's going to oxidize hydrogen gas. Hydrogen gas is going to be oxidized to H+, and then the electrons are going to flow through the circuit. What kind of voltage do we generate? We generate 0.340 volts. And so what we're going to do is we're going to keep this simple. We're going to say that all that voltage is due to copper 2 because the hydrogen is going to provide or be arbitrarily set at 0. And so if I do this, then the equation for this particular cell is going to look like this. E of the cell, which is going to be 0.340 volts, is going to equal E for, well, I'll write it left to right too. We're going to have E of the anode. This is going to be under standard conditions because everything's 1 molar, 1 molar, 1 atmosphere in this case. You know, it's either 1 bar or 1 atmosphere, depending on who's doing it. And Petrucci switches around, so we're still going to call this standard. And it's going to be E of the anode plus E of the cathode. Okay, E of the anode is, well, the hydrogen is supplying the electrons, and it's going to form H+. So this is a shorthand way of writing that. Hydrogen supplying the electrons, and when hydrogen gives up electrons, it forms H+. We call this an oxidation reaction or half reaction. The half reaction would look like this. H2 gas goes to 2H plus 2 electrons. Over here at the cathode, we're going to consume those electrons. At the cathode, copper 2 is taking the electrons to deposit copper solid. And so the half reaction over here is copper 2 plus 2 electrons yields copper solid. And so, you know, what it is going to be a combination of these potentials. The cell potential is a combination. I don't like to use the word difference. I like to use a combination of these. Now, the hydrogen is arbitrarily defined as 0 volts, and therefore the copper 2 to copper will be 0.340 volts. But that's going to lead to a huge error because is it really 0 volts to oxidize hydrogen? No. But what it leads to is a systematic error. And so on one side, all the anodes are going to be systematically off in one direction. And then all the cathodes are going to be systematically off in the opposite direction. And what's going to happen is they're going to be equal and opposite. So when you add these two together, the systematic errors cancel each other out, and you get the correct answer, 0.340 volts for this. Now, this is what happens if I try to set up the same thing. I'll put the SHE, or the standard hydrogen electrode, on the left, and in this case I'm going to put Zn2 plus and zinc on the right here. But what's going to happen here is the SHE now is going to be the cathode, because Zn2 plus is not strong enough to oxidize the hydrogen gas, whereas H plus is strong enough to oxidize zinc. And so H plus is going to be pulling electrons on the platinum. And the platinum's in electrical contact with the zinc, so eventually the zinc is going to be oxidized, and those electrons generated will be sent over here. And so by convention, this is written backwards. But we'll leave it like this, because what this is going to do is it's going to generate what we call a negative potential here for the zinc. And the zinc is going to be a negative potential because in this case zinc is being oxidized, right? Zinc is being oxidized, but if zinc were the oxidizer, right? If zinc were the oxidizer, it has a negative potential, negative 0.763 volts here of potential. And the reason why is this. We're pretending that zinc, you know, the cathode is supposed to be written on the right, and so we're pretending that the Zn2 plus is the oxidizer. If the Zn2 plus is the oxidizer, the electrons flow from left to right. And so the Zn2 plus should get the electrons and deposit zinc metal here, and the electrons should be coming from hydrogen gas, which forms H plus. But that's wrong. That's wrong. So if we set up a cell like this where we think the electrons are going to go left to right, they actually go backwards, right to left. And the voltage is actually positive because what we're doing is we're oxidizing the zinc, we're not reducing the zinc. So all we have to do is we flip the cell the other way and we reattach the leads, because the leads were attached backwards. The red lead to the black and the black lead to the red. And so this voltage, I mean, all we have to do is flip this, and then we'll get the positive voltage, which shows that H plus is the oxidizer in this case, and H plus is the cathode. And so when we look at these potentials, we generate a chart like this, all relative to the arbitrary zero. So we attach the SHE to a whole bunch of others, and we can generate all these numbers here by measuring the voltage. We take a look at the SHE here, and the SHE shows 0 volts. That 0 volts, what does it mean? Does it mean there's no potential there? Does it mean that H plus is not an oxidizer? No, the 0 volts is just arbitrary. And so it means nothing. And it just means it's hydrogen. And so what we have, hydrogen ions or hydrogen gas. So what we have is this, if we have a positive voltage in this chart, it means it's a stronger oxidizer than H plus. If we have a negative voltage, it means it's a weaker oxidizer than H plus. So zinc has a negative voltage. That means that H plus should be the oxidizer, zinc metal should be the reducer. All right, so what Petrucci does is he does something what I think is funny. He has the cathode potential minus the anode potential, whereas I have the cathode potential plus the anode potential. What's the difference here? What the difference is this. So I have E of the cell is equal to E naught of the cathode. And what happens at the cathode, oxidation or reduction? Reduction. So this is going to be E naught of the reduction potential. And then I have it plus E naught of the anode. At the anode, what happens? Oxidation happens at the anode. And so what I do here is I add up the reduction potential plus the oxidation potential to get the cell potential. What Petrucci does is this. Petrucci does it this way. He takes the cathode like this. And it's the same thing, plus the anode. So Petrucci does the same thing. It's E naught of the cathode plus E naught of the anode. Where the negative sign comes in is like this. The negative sign comes in because what he does is he takes the reduction potential. That's correct for the cathode. But at the anode, what happens? At the anode, oxidation happens, but what Petrucci does is he adds the negative of the reduction potential for the anode. And so what he ends up with is he ends up with E naught reduction minus E naught of reduction. And so you can't have reduction without oxidation. And so what he's doing is he's subtracting two reduction potentials, but the reason he's subtracting two reduction potentials is to convert one of the reduction potentials into an oxidation potential. And so what he wants to do here is this. He wants to use this table as is. This is a table of reduction potentials. And so if I were using this and I reverse this reaction, when you reverse this reaction here, you just change the sign. And so what I'd rather have you do is to reverse the reaction and change the sign and then add them. What Petrucci has you do is he doesn't have you reverse it, he just has you use both reductions and then subtract one of them. And so that's a little bit more confusing. But once you do that, then this table is very easy to use. And so let's do some calculations here. And so let's look at this cell here. And so this is the way we'll do it. If I want to calculate E of the cell, although it's given, we can calculate E of the cell by just adding up the anode potential plus the cathode potential. At the anode potential, I have zinc goes to zinc solid. Okay, where I get this little symbol, Zn, vertical line Zn, this is Zn, Zn solid to Zn2+. Where I get this is from here. This little thing here, this is called the cell diagram. Even though, you know, this drawing looks like a diagram, we don't call it a diagram, we just call it a drawing. This is a cell diagram, and the cell diagram is a shorthand way of describing this cell. And so the anode's always written on the left. We have zinc solid going to Zn2+ in this beaker. This double line represents the salt bridge. And then over in the other beaker, we have the cathode. At the cathode, we have copper 2+ going to copper solid. And so this is the cell diagram, or the shorthand representation of this cell. If we want to calculate the cell potential, then what we do is we add up the anode plus the cathode. And so the anode is Zn, goes to Zn2 plus. The cathode is copper 2 goes to copper solid. There. Okay, then we go to the chart. And we look it up. Okay, Zn going to Zn2 plus is the reverse of this reaction. If we reverse this, it's no longer reduction potential. These are reduction potentials. It turns into an oxidation potential. As an oxidation potential, all you have to do is change the sign here. And so the oxidation potential of Zn is plus 0.763 volts. That's Zn going to Zn2 plus. Okay, then we look for copper 2 going to copper. Here's copper 2 going to copper. This would be a reduction potential. So copper 2 goes to copper is in the correct order, and that's plus 0.340 volts. So we just add these two up, and we get 1.103 volts. All right, this is how you do it, or you could do it via Petrucci's method. Do you want to do it via Petrucci's method for comparison? No? You'll be confused? All right, I'm going to skip it then. You don't, just ignore the Petrucci method calculation. Just do it this way then. Let's do another example. Okay, if we look at this cell diagram, it's a little different than the other. This cell diagram shows platinum, but does platinum participate? Is platinum oxidized? You know, over here we write the anode, right? And the anode is where oxidation occurs. The anode is where electrons are being generated. But what does the platinum do? The platinum is the conduit in which the electrons are being fed into the external circuit. And so the platinum is what we'll call the electrode. The electrode in this case is inert. The electrode doesn't participate. All the electrode's job is to take the electrons that are generated from hydrogen being oxidized to H+. So hydrogen gets oxidized to H+, those electrons have to go somewhere. The electrons are going to go in the platinum electrode. From the platinum electrode, they're going to travel over to the copper electrode. Copper electrode has two jobs. One, copper electrode feeds the electrons to copper 2. But copper also is a product. And so this electrode participates in the reaction in that it's a product of the cathode reaction. But if I want E naught of the cell here, I'm going to do it different than Petrucci, because Petrucci has this. He has the cathode minus the anode. I'm not going to do that, right? We'll just write it as written, because by convention, we write the anode on the left, the cathode's on the right. The anode's where we generate the electrons. The cathode is where we consume the electrons. And so in this particular reaction, E the cell, this will be under standard conditions like that. E the cell is equal to E naught of the anode plus E naught of the cathode. The anode is, what are we doing? We're taking hydrogen and going to H+. Is platinum critical? Could we have used gold? Yeah, we could have used gold, we could have used graphite, we could have used any other material that doesn't really react with H+, and there are lots of them. In fact, we could have even used copper. And so platinum is not critical. We don't have to put that in there necessarily. So hydrogen goes to H+, and then over at the other electrode here, copper 2 goes to copper metal. And so here we're going to have reduction. Over here we have oxidation. This is a hydrogen gas over here. And so I'm writing it in the shorthand way. And then we look it up in the chart here. So let's take a look at the chart. The copper 2 goes to copper is plus 0.340 volts. And then hydrogen is backwards because hydrogen gets oxidized. These are all reduction potentials, so oxidation potentials are reversed. So hydrogen gets oxidized to H+. What do we do? Well, if we flip this reaction, or if we go backwards here, we have to change the sign. So rather than being plus, it would be negative, but it's 0 anyway, so it doesn't matter in this particular case. So hydrogen goes to hydrogen plus would be like this -0, but it doesn't really make sense. Volts. Plus 0.340 volts, which is going to give us 0.340 volts. And so calculating standard cell potentials is really easy. All you do is you just add the two, except you have to flip one of those. Because our table is just reduction half reactions. And so we need oxidation and reduction, and therefore we have to flip one of them. We have to flip well, which one does oxidation occur at? Does oxidation occur at the anode or at the cathode? At the anode. And so again, this would be, the oxidation plus the reduction potential. All right, any questions on this here? Okay, let me just show more cell diagrams. Here's the cell diagram for this. This is the one we made in the lab. And so over here we have the anode. Oxidation occurs at the anode. Electrons are generated. So we go from zinc solid to Zn2+. The electrons will travel. Okay, but where do the electrons go here? Well, it turns out that zinc acts both as the reactant and the electrode. And so as the electrons are being generated, they can be passed on to the remaining zinc. The zinc passes those on to copper wire. This copper wire passes the electrons to this electrode. This electrode has to be an inert electrode, so you could have used graphite here. If you use graphite, you'd have another element here, carbon. Or you could use platinum here. If you use platinum, then what we do is we put a comma here and then platinum. A comma because a vertical line represents difference between phases. So this is solid phase, this is aqueous phase. If I use graphite here, let me rewrite this cell diagram using graphite. If I use graphite here, like some of you might have done in lab, what we would have done was we would have put in a comma here rather than a vertical line because there's no difference in the phase. So both of these are solid, I should say solid graphite. Since they're both in the same phase, we use a comma. So whenever anything's in the same phase, you use a comma. When they're in different phases, you use a vertical line. And so this is showing this, that copper 2 takes electrons to form copper metal. Those electrons are being fed from zinc to graphite. The graphite's giving the electrons to copper 2. The copper 2 in turn is depositing copper, and those copper will deposit on graphite. Does that make sense? Okay, if you didn't use graphite, then we just use copper metal, and so copper metal serves two purposes. One, it serves to feed the electrons to copper 2, which is an electrode. 2, it's the product of this redox reaction, which is a reduction half reaction. So we got our oxidation and reduction half reaction. And so this is another example of a cell diagram. A cell diagram is a shorthand representation of this cell, which we see in this drawing up here. And so on a test, I might ask you to write the cell diagram. If I ask you to write the cell diagram, I'm asking you to write this. If I ask you to draw the cell, then I'm asking you to come up with some drawing like this. All right, that's it. We're going to move into the computer lab next and finish up that one experiment. I'll post this PowerPoint on the Piazza. Probably going to be emailed.
Would that be too messy?
No.
That was
Forgot to add this to
What is for the? Oh yeah.